Okay, so I suppose I get started with this. So I welcome you all to this problem solving and live interaction session for week 7. Today we'll be discussing the contents of week 7 from the experimental stress analysis course being offered on the Swayam portal. My name is Ganesh Ramaswamy. I'm a PhD scholar pursuing PhD under the guidance of Professor K. Ramesh, who happens to be offering this course. And my co-guide is Professor U. Saravanan from the Civil Engineering Department. So if there are any questions from what we discussed previous weeks, I would urge you to ask. Unless there are no questions, in which case we can proceed with solving the questions of this session. Okay, so I take it that. All right, so let us proceed with the first question of the day. The preferred material for studying the effects of body forces using photoelasticity is which of the following? Plexiglass, epoxy, gelatin, or glass? Now, what we need to understand here is all these materials, they are all birefringent. Yeah, birefringent under stress. Now, the only thing is the response varies from material to material. Now, if we see in terms of F sigma, if F sigma is high from stress optic law, we know that sigma 1 minus sigma 2 is n F sigma by T or H or whatever. In which case, if I take sigma 1 minus sigma 2 at a point to be some constant k, it implies that it is n F sigma. So we can see that this is a rectangular hyperbola, which implies that if F sigma is very high, n will be very low, which implies that your optical response will be very low. Optical response will be low. So in cases where we want to see just by its own self weight what are the effects, desirably F sigma has to be very low so that it gives a high response. So if we were to arrange these in terms of increasing F sigma, as so we can see that gelatin has the least F sigma, it's around 0.1, which is followed by epoxy, which we know is around 12, and then followed by plexiglass, which is around 140, which is quite high, considerably high. I'll just put it here. Yeah, which is followed by glass. Glass is a classic example of very poor birefringence. So it doesn't show any fringes, because of which we need to go for carrier fringe analysis and all that. So understandably, to study the effect of body forces, including self weights, gelatin is the most preferable because it will give high optical response even for a minute stress. So whatever, yeah, Shubham, whatever had pointed out, it is absolutely right. So yeah, let us look at the next question. In the 10-step phase shifting method, the 4 isoclinic images captured are which of the following? Which combination is what is being asked. So just to give a brief, essentially in photoelasticity, we get contours of principal stress difference sigma 1 minus sigma 2 equal to k, and theta p equal to k, k1, k2, let us say. So these two isochromatics and isoclinic fringes we get, which implies that at each and every point we can discern principal stress difference and isoclinics, that is principal stress orientation. Now, from conventional photoelasticity, we know that at each and every point, either we can see by doing Tardy's method of compensation as to what the fringe order is at that point. For conventional photoelasticity, For conventional photoelasticity, for isoclinics, we basically rotate crossed polarizer analyzer combination. We rotate it till it passes through our point of interest. So essentially, when we go for this, we ideally it becomes a point by point technique sort of. And for delta or n, what we do is we can do Tardy's method of compensation, which, if you remember, is nothing but first we identify the isoclinic angle at that point, then set the entire circular polariscope at that isoclinic angle and just rotate the analyzer so as to introduce artificial known retardation, which we will subtract out once our fringe of interest reaches the point of interest. So this is what is done in conventional photoelasticity. Now when we go to digital photoelasticity, which is nothing but we are replacing our human eye we are replacing our human eye with a digital camera, and we are doing image processing with CCD acquired images so as to get isoclinic and isochromatics at all the points in our domain. So these I'm sorry, this is not. So this is photoelasticity. In digital photoelasticity, we basically calculate theta p. We can calculate using the technique of phase shifting, which essentially involves Jones calculus. What we do is that each and every optical element, we don't fix the orientation, but we take it to be some arbitrary orientation. And then we write the Jones calculus and determine the exit light intensity equation. Once we do that, there are basically only three unknowns. That is, one is isochromatic, one is isoclinic, and one is the background intensity that is coming in phase shifting techniques. But there has been a lot of research in this area, and they have found out that by optically subtracting or adding and manipulating certain images that have been acquired using arbitrary orientation of the polarizers, the analyzers, and the quarter wave plates, we can actually obtain theta p and retardation at every point. That is the basic tenet of phase shifting method. So isoclinic angle at every point can be obtained by phase shifting methods. Essentially, what we will be doing is we will be taking 4 images of plane polariscope arrangement and then doing some manipulation over it in order to mathematically playing with intensities of at each and every pixel in order to obtain theta p. Whereas when we go to delta, when we go to retardation, we have again phase shifting we can do, where the 10-step method is well established for obtaining. Basically, we will be taking 4 images with our plane polariscope arrangement with different configurations in order to obtain theta p. Then that will be followed by 6 more images of circular polariscope with some specific orientations which have been carefully chosen in order to minimize quarter wave plate error and keep the quarter wave plates crossed and all that. So once we do that and do the same intensity subtraction addition, we will be able to discern what the isochromatics are at each and every point, which is nothing but discerning n, so delta by 2 pi. Another way to obtain delta is by a lookup table. For example, you take an image of a known problem. For example, you develop a color calibration table as it is shown in the lecture. Once we do that, and let us say that now you have obtained your application image. Basically, at each and every pixel, we will be running a least squares difference error, and we will be seeing where that error is minimum in order to discern what the fringe order it is at that point, which is basically nothing but matching your RGB. Matching red, green, and blue intensity, light intensities at every pixel in the model domain against a color calibration table. So this is also called TFP. 3 fringe photoelasticity. So this is the basic background. I just wanted to mention this once. So for phase shifting, in order to obtain theta p, we note four isoclinic images, and these are in plane polariscope arrangement. So if we see the 10-step method, basically it will be having four arrangements where I'll just give you the analyzer. Analyzer angles would be 0, pi by 8, pi by 4, and 3 pi by 8, which is nothing but 0, 22.5, 45, and 67.5. So this has been discussed well in the lecture. And even for the problem of a disk for a ring under diametral compression, the images pertaining to these particular arrangements are shown. So if someone were to actually try out phase shifting method, they can just take a snip of the screen and load it in MATLAB, and you can try adding and subtracting as per the formulae given in the lecture in order to discern what the isoclinics and isochromatics are at each and every point. So I hope that that is clear. So if there are any questions, please ask. Yeah, so what I was saying was, Mr. Rajamanna, see, now we have our analyzer and polarizer combination crossed in case of a circular polariscope. So essentially our polarizer angle, if we see, it will be that whatever is analyzer plus 90. So this will be pi by 2 and so on. So if this is 0, polarizer will be at 90, analyzer will be at 22.5. Then at 0. Then when analyzer is at 0, 22.5, polarizer will be 90 plus 22.5. It will go like that in a crossed combination. Yeah. Okay. So I hope that that is clear. So that is the basic tenet of our phase shifting method. Yeah. So which of the techniques is widely used technique to study the stresses interior of a model conveniently? Yeah, exactly. So photoelasticity in case of 3D studies, since we are dealing with transparent materials, there are two ways to go about it. One is by stress freezing and slicing. And the second one is it employs the concept of optical equivalence, which is nothing but you put a three-dimensional model and load it in a polariscope. Once there will be three unknown parameters, essentially the model will be introducing rotation and retardation at each and every point along its light path. So we will integrate what the effects are over the depth of the model along the light path, and we will substitute it with an equivalent rotation and rotator and retarder combination so that we get the same response. So this is the basic tenet of optical equivalence, which is employed in integrated photoelasticity. It's quite demanding mathematically. So that is the integrated photoelasticity technique. So essentially these two methods give you a via media to obtain stresses interior to a model. Now in DIC, in digital image correlation, presently there are techniques where you can do volumetric correlation, where there are studies which can even measure displacement interior to a model, but it's a maturing field as of now. Okay, so I hope that this is clear. So are there any questions at this stage? Okay, so I take it that it is clear. So let us move on to the next question. If I1 to I4 represent the intensity recorded using a plane polariscope, I1 to I4 are a plane polariscope, I5 to I10, 6 in numbers, represent the intensity recorded using a circular polariscope in the 10-step phase shifting method. The isoclinics over the domain can be determined by which of the following equations? So essentially what we have to look out for is the first four plane polariscope combinations arrangements give us theta c, theta, essentially theta, yeah. And the last six circular polariscope arrangements give us delta. So essentially we have to look out for formulae that employs only the first four, which we can clearly see it is nothing but the first one, because all the others are having circular polariscope arrangement images as part of them, which is not viable. Essentially, how this works is once we do the Jones calculus, to get the exit light intensity, what we will do is let us take the polarizer at 90 degree, and let us take the first quarter wave plate slow axis at say 3 pi by 4, and let this be at 90. Now we have the model here, and then we have our second quarter wave plate. This is slow, and this we will be taking at some arbitrary angle neta, and the analyzer with respect to the datum we will be taking at some other let us say beta. So now we will be doing this Jones calculus analysis and obtaining the exit light intensity in terms of as functions of beta and neta. So this will essentially come out to be some combination along with theta, functions of neta, theta, background light intensity, then we will have theta and delta. Now the idea is to add or subtract using basic trigonometric equations in order to get how to eliminate all the others except for theta. So once we do that, essentially when we subtract I4 minus I2 by I5 minus I6. So essentially this will be giving us nothing but tan theta p. It will be sin theta p by cos theta p. When we take tan inverse of that, and it will actually give us 4 tan 4 theta p if we work out the equations. So essentially theta p will be nothing but 1/4 tan inverse of this thing. So it is easier said than done there, because tan inverse trigonometric functions, as we know, they are multi-valued. So this will lead to some jumps in our analysis. Once we obtain our isoclinic angles with jumps, when we apply the phase shifting techniques to obtain our isochromatics, namely delta, so that will also have this error percolating into it unless we do unwrapping. So there are a lot of algorithms that have been developed. Even our professor has contributed that in a huge way. So these algorithms can be used in order to do unwrapping over the domain. And now this phase shifting technique, the 10-step method, is quite standard and has been applied to quite a lot of problems in order to obtain accurate theta and delta over the domain for stress separation studies. So I hope that this is clear. So if there are any questions at this juncture, please ask. Okay, so I take it that that is clear. Yeah, so using phase shifting techniques, one can obtain information regarding which of the following. So anyway, we know that delta and theta can be measured. And there are algorithms and ways and means to obtain stress separation also. So phase shifting, once it is done accurately, can be used for stress separation studies. Stress separation in problems. So this also is possible to achieve. So what are the stresses in case of plane problem, planar problem? Essentially, we have sigma x, sigma y, tau xy, which translate to in some orientation they translate to sigma 1 and sigma 2. So essentially, normal stress component and shear stress components also can be determined using phase shifting techniques. So there are ways and means to do that, which have not been covered in the present lecture, but nonetheless it has been referred to and it has been clearly mentioned that phase shifting finds an application in stress separation once it is done accurately. Okay, so let us look at the next question. When the body forces and Poisson's ratio mismatch is neglected, when this is neglected, plastic models can be used for analyzing 2D problems in photoelasticity because essentially, why are we using plastics? So, because plastic exhibit birefringence, yes, and in case body forces and Poisson's ratio mismatch is neglected, this is for a 3D case. In case of planar problems, if we have constant body forces also, our equilibrium equations and our compatibility equations will not have the material properties coming into the picture, in which case stresses would essentially be the same irrespective of the material. So they are easy to visualize as the elastic constants have no influence. Yes. So stresses, we can easily see what kind of stresses in a similar metallic plate would exist in case the loads are applied. Strain distribution would be same as the prototype. This needs to be qualified a little. So stresses being independent of elastic constants does not imply that strains are same. So this is not exactly correct, because even in the lecture, if you see, if when professor is holding a aluminum disc versus a polyurethane disc for the same load, we will be able to see that it will deform more because of its less stiffness. So strain and displacement essentially will not be the same. Although for applying for 3D photoelasticity, for stress freezing techniques and all that, we should ensure that we do not overload the model. Just because the stresses are same, we should not load the model in such a way that our prototype loads and model loads are equal, in which case we will again go for strain equivalence. So that is the tenet of basic principle behind our similitude in case of photoelasticity. So strain distribution essentially does not remain the same in the model as compared to the prototype. Loads can be applied. Loads to be applied can be calculated using similitude equations. Yes, exactly. So similitude equations would be our strain in the model equaling strain in the prototype. Why, with us specifying these conditions, we can essentially figure out how we have to scale down the models, scale down the loads that are to be applied to the model. Yes, stress and its distribution is the same for as in the case of prototype. Why is this so? Because our distribution involving Poisson's ratio. In the case of 2D, it doesn't matter. It doesn't appear in the equation. Even in the case of three-dimensional analysis, only Poisson's ratio shows up, which influences the distribution. Unless if the question qualifies that the Poisson's ratio mismatch can be neglected. For example, if we were working with polyurethane, which has a Poisson's ratio is around 0.28, and for metals also it is in this range. If this minor mismatch is neglected, then essentially we can see that stress and distribution is the same for the model as given for the prototype. So this holds, this surely holds. So I hope that this is clear. Are there any questions at this point? Okay, it's clear. Fine. Thanks. Okay, so let us move on to the next question. Using a white light source is advantageous compared to monochromatic light source because of which of the following? It can be used to calibrate polariscope to determine the association of polarizer analyzer axis to the major and minor principal stress directions using a color code. Is this true? Yes, exactly. So once we take, for example, let us take a beam under 4-point bending. And if we just take the sections where we have fringes equally distributed, so we'll be able to see that these will be our fringes. It is linearly varying. So essentially, this is what we will be seeing. So if we take a monochromatic image, we will just be seeing white and black bands in periodically, which are equidistant. So it is not possible for us to essentially quantify which fringe order is where is it existing. Yeah, so it will not be possible for us to quantify which fringe order is existing where. However, if we were to replace this with a color, that is, if we were to replace this with white light, then we would be able to see that, for example, this will be somewhat different in color. So we will be able to see color variation across fringes. In which case we can develop color calibration tables for a standard model. Once we do that, we can apply the same to a unknown problem. So it can be used to calibrate the polariscope to determine the association of polarizer. I'll just briefly explain what we are trying to achieve here. Let us say that we have a plate with a hole. Now, in case of plate with a hole with a far field stress of sigma that is applied, we know at these 2 points for the assumption of that infinite plate holding, the stresses would be 3 sigma. Sigma theta theta would be 3 sigma. And at these points, the stresses would be sigma theta theta would be minus sigma. So it is interesting that once we pull it, we have a compression that is being applied. Now, if let us say that we did not know this problem a priori, and we just know the fringe orders here. Now, our idea is to find out whether the sigma 1 minus sigma 2, whether it is pertaining to the maximum principal stress or minimum principal stress. That is, the once we place an isoclinic here, it will give us theta p. Theta p will be related either to the minor principal stress or major principal stress. Now, in case that we want to determine as to which theta p this is, whether it is pertaining to major or minor, what we can do is we can take a model of known. Let us say we have a stress frozen model where we have applied uniaxial tension. First, we will place this in the polariscope and try to do Tardy's method of compensation with this. We know for a fact here that our principal stress is sigma 1 minus 0. Principal stress difference is NF sigma by T, because this is under uniaxial tension. This doesn't have a hole. This is just a specimen we take. So now when we do Tardy's method of compensation, we know sigma 1 what it is. Now when we do, we can actually see whether n is increasing or decreasing. Upon Tardy's method, we can figure out whether n increases or n decreases. So based on that, we can discern whether this pertains to, let us take this as the basic information about the polariscope arrangement currently we have. Then take it to this problem and do the same thing. Now we know that at this point, our tension is existing. And if we were to rotate the analyzer to actually account for the Tardy's method, then we would be able, if we are able to see a similar response, we can infer from what we saw in case of uniaxial tension specimen that our isoclinics pertain to that is the major principal stress direction. That is, our polarizer is aligned with the major principal stress direction. And when we have the analyzer crossed, we will be able to see a fringe there. There won't be any light exiting. So this is the basic principle with which we basically calibrate polariscope in order to arrive at whether this is pertaining to the major principal stress or minor principal stress. So yes, this can be done. Sign of the boundary stresses can be identified using a color code. So let me just elaborate on this a little bit. Let us say that we have this problem at hand. In case of a 4-point bending, I'll just copy this. Now I can see that at the boundary, top boundary, let us say that it was applied with a moment like that. Now I know that my top face is in compression and my bottom face is in tension. So on the top face, if I take this to be my axis, let us say this is X and this is Y. I know that the top and bottom faces are free surfaces. So only sigma X can exist essentially. That is because our normal vector goes in the Y direction. So for any surface, the stress component that can exist in the stress tensor can at best be tangential to that free surface, which we have discussed in quite a lot of detail. So we know if we were to arrange that, sigma y is 0, sigma x is let us say minus m by z. Okay, so we know that how there is no shear existing because it's a free surface. Hence, this makes these the principal stresses, which implies that sigma 1 for this case is 0 and sigma 2 for this case is minus m by z, because we arrange it in algebraically decreasing order. So in which case sigma 1 minus sigma 2 will be 0 minus m by z, which is nothing but m by z, something a positive quantity, will be n f sigma by t. Okay, so this is for the first case. Now what we do is I apply with some external means. Let us say that I apply a point load here, a compressive load here. So at that very point, let me draw this clearly. I apply a load. So what happens in this case? I'll take this to be the case 2. Okay. My idea is to determine at this point. So what I'll do is I'll apply a compressive force there. Now at this point, if I again were to analyze it, I'll be getting sigma 1 equal to, there is some compression that is being applied. Let us say this will be sigma y. Sigma y will be some known compression. Let us say minus uh, sigma a, and then sigma x will still remain the same, minus m by z, let us say. So depending on the magnitude, let us say that I have applied it with a known quantity, which is just about uh, less, but nonetheless it is compressive. In which case, sigma 1 minus sigma 2, now this will get affected. Sigma 1 minus sigma 2 will be, let us call this sigma 1, sigma 2, knowing fully well that I have applied a load that is compressive, but nonetheless less than this. So it will be minus sigma A minus m by z, which imply m by z minus sigma A, which will be n1 f sigma by t. So earlier it was n, now it is n1. Keeping f sigma and t constant, I can see that n1 reduces. As compared to n1 is less than n. So once I apply that load, if the fringe order decreases, because I have a color calibration table with me, I can see that uh, there was one color earlier. Now when I have applied the compression, the gradient, the color has changed and it has gone to a lesser fringe order. If that happens to be the case, then I can discern that what is the nature of the stress that is being applied at that free surface. So this is the entire technique behind this thing. Now it might not be possible to always pinch and apply a load, in which case we can use a stress frozen specimen. For example, if we take this to be a stress frozen specimen with known uniaxial tension and we just hold it straight, perpendicular and parallel to a free surface, we will be able to discern based on how the fringes actually come out to be. In when you hold it parallel and perpendicular, we'll be able to conclude whether the fringe order there is more or less and infer whether the tangential stress that existed at that free boundary is tensile or compressive in nature. So I take it that it is clear. If you have any questions, please do ask. So sign of the boundary stresses can be identified easily. Whereas this is not possible in case of a monochromatic image. Why? Because it will be black and once you bring the fringe order, it will move. Nonetheless, there will be some optical response in form of the movement, but you won't know what the gradient is, whether it has increased or decreased, because both will be captured in that movement unless you know the specific color, how it has changed. So that is why white light source would be more advantageous in this case. Can be used to identify whether fringe orders are increasing or decreasing in a particular direction. So what does this mean? Essentially, this gives us gradient information, or I should say n gradient information. Now, if we take a disk, essentially we'll be able to see that once we get closer, we'll have fringes such as this. If we were to do the same with plate with the hole where there are multiple reversals of gradients, we'll find it much advantageous to use a color calibration table to discern whether it's a downward gradient or an upward gradient. So yes, this is definitely there. Subtle changes to stresses can be observed in case of white light source as opposed to monochromatic light source. To actually make this point, Professor in the lecture he has shown one stress frozen disk which has a hole drilled in it. Once this is stress frozen, there is a hole that has been drilled into this model from where a fringe passes. Essentially, a fringe passes through that point. Now, if you were to see in the black and white, in the monochromatic image, there won't be much distortion and the fringe would somewhat be continuous. Whereas if we look at the same specimen in a colored field, that is in a white light polariscope, we'll be able to see that the distortion show very much clearly in terms of color. So this is very, very sensitive to that. So essentially, even if we use a single wavelength, we might not be able to discern much information about these residual stresses that have been brought in or subtle changes to the stress field, which becomes very apparent in case of white light source. So it is quite sensitive to that. So yes, this is very much true. So all the four options are highlighting the advantages of white light source compared to a monochromatic light source. So are there any questions at this point? I'm sure uh, there would be. Okay, all right. So okay, so if it is clear, then it's great because I felt that I was not very articulate about this, but it's okay. If it is clear, then it's fine. All right. So in that case, let us move to the next question. Arrange the steps given below in the correct sequence for analyzing a 3D model using photoelasticity. So essentially, these are pertaining to stress freezing. In stress freezing, what we basically do is, let us say I'll explain with the term, with the example of a disk. If I were to take a disk, so this is at room temperature. Now, once we take this, we'll apply it with loads which need to be recalculated for a appropriate response at its annealing temperature. So what we will be doing is we will be subjecting it to a thermal cycling process. Once we it will basically look something like this. So essentially, first we have to heat it at with the loads applied. We have to heat it at a particular rate of temperature increase. Then we hold it constant for some time, and then we let it drop gradually to room temperature again. And throughout this process, the load should be applied. Once it comes back to normal temperature, even upon the removal of loads, we will be able to see that the stresses get frozen inside that model. If we were to take this and place it in the polariscope, we even without any load, we will be able to see the patterns that we see in case of a compressive force, in case of two diametrically opposite compressive forces applied to a disk. So this is the basic this thing of stress freezing. Now, because it is a disk, we can directly see it. If it were a complex model, we know that in case of photoelasticity, it basically gives us only stresses that are perpendicular to the light path. In which case, if we want to discern that what is the distribution here, let us say along this line. So what we would be required to do is we would be actually cutting a slice out of this. This slice we will cut out and place it in a polariscope, and we will be able to see in that plane whatever we have cut in that plane how sigma 1 and sigma 2 are interacting. So basically while slicing we have to be very careful so as to not introduce any machining stresses into the model, because that could affect and bring in spurious fringes which could throw your result off. But rest assured that once we have done the stress freezing process and the slicing has been careful with the use of coolants and all that, we can take those slices, place it in a polariscope, and take a series of images along the depth of the model. Once we take these, we can process them using either by phase shifting or three fringe photoelasticity, as we saw. So at each and every point in that slice, we will be able to discern what theta is and what delta is. So essentially, at every point, we have the principal stress difference and isoclinic angle. So then we can appropriately stitch it with having some benchmark. We can stitch it and get a three-dimensional picture of the entire stress field that is existing due to that load in that model. So towards that, because the loads need to be carefully applied, we need to actually check how the properties are of that material, of that photoelastic material at the thermal cycling temperature, because this will be of the order of 90 to 120 degrees. So at 120 degrees, the properties won't be the same as that existing in the room temperature, in which case, if we were to apply the same load that we applied at the room temperature, the models would break. So we need to account for that variation also. This can be further effectively used by appropriately selecting the material. So towards this, if we were to read these options, the fabricated parts are assembled to form a 3D model. The slices are cut from the model along the loading plane where the stress is maximum. Model is subjected to a thermal stress freezing cycle. The parts are made using a suitable photoelastic material. A suitable force is applied to the loading mechanism. View the sliced model in the polariscope. So we can see that we'll start with the selection of a suitable material. Once we select a suitable material, we will calculate the force that needs to be applied here. Okay, so I take it that this is not given anywhere. Why? If it starts with 4, what are the other options that can be done? Unless we, okay, this implies a assembly. Essentially, we are dealing with a multiply connected body. So the fabricated part needs to be assembled to form the 3D model. If we see the lecture, it is shown one of the models which has been used in some aerospace industry. It has 3 components. Those 3 components have been fabricated separately using photoelastic specimens, as photoelastic specimens. Then they were arranged, and then they were appropriately loaded and subjected to this thermal cycling process, taken out, carefully sliced, and viewed in a polariscope. So that is the basic essence of this. So yes, definitely we need to assemble them and then calculate a suitable force that needs to be applied. Once the forces have been applied, we will subject it to a thermal cycling process, which will be followed by 3. Now the thermal cycling is completed. So this needs to be cut into thin slices in order for us to view it in a circular or plane polariscope. So essentially this will be followed by 2. We will cut it and then view it in a polariscope. So if I were to just write this out, it will be material selection, fabrication and assembly, similitude calculations, and application. Once this is done, thermal cycling. Once this is completed, slicing and view. So slicing is followed by viewing it in the polariscope, and we can take images of them as we do in the case of our normal two-dimensional photoelasticity and process them, and towards the end stitch them up together in order to complete the study. So I hope that this is clear. In case there are any questions, please do ask. Okay, so I take it that this is clear. Let us go to the next question. Select the correct statements related to integrated photoelasticity. It depends on the principle of optical equivalence. It falls under the category of scalar tomography. It falls under the category of tensorial tomography. The 3D model is replaced by a retarder and rotator combination. So yes, as we discussed, it depends on it. Essentially, it is founded on the concept of optical equivalence. That is, whatever optical response a three-dimensional loaded structure introduces, we will replace it by known rotator and retardator combinations for each and every plane and do back calculation in order to match what the exit light characteristics were and what the input light characteristics are. In which case we will be able to deduce what the stress field along the light path has been. So this is the basic tenet of integrated photoelasticity, which is based on optical equivalence. So even in the lecture, it is said that it is essentially dependent on tensorial tomography. That is, at each and every point, we are determining not one but six components, six independent components of stresses. So it definitely is quite a lot more involved than scalar tomography because it is calculating six directional dependent points, quantities at each and every point in the model domain. The 3D model is replaced by a rotator and retarder combination in order to find out the characteristics of, or rather match characteristics of exit and incident light. So this will be done by first assume a stress variation along the light path. So these we will assume based on some unknown coefficients, and based on the error analysis of optical equivalence, we will be back calculating those coefficients in order to essentially arrive at one combination which will give the same optical response as compared to the 3D response of that model, in which case now our assumption has been refined, and that is the stress distribution along the light path. That is the basic principle behind it. So yes, this is dependent on. So I hope that this is clear. Okay, so let us look at the next question. This has to do something with similitude. A turbine blade is subjected to a load of 1000 newtons, and for geometric similarity, the characteristic length can be taken as 15 centimeters. An epoxy model of the blade having a 7 centimeter characteristic length is used to analyze the whole stress field using photoelasticity. If Young's modulus of steel and epoxy are something, what load in Newton must be applied to the model to get geometrically similar deformation, neglecting the Poisson's ratio mismatch? So essentially, if we see, experiments can be done on models which can be scaled down or prototypes. So here the prototype is, we have our turbine blade which is made of steel. So the material here is steel, and the material we are trying to study that with is epoxy. So for that, the characteristic length, let me call that L. Let me denote that by L. So I can see that the characteristic length of my model is given to be 7 centimeters, and the characteristic length of my prototype is given to be 15 centimeters. So I am essentially scaling it down. The load to be applied for the model, let me denote that by some other letter. Let us say P. P model is 1000 newtons. I'm sorry, this is P prototype. Okay. P model is what we are trying to determine. What is the load that should be applied so that the deformations are geometrically similar? 7 Newton. Okay, so we have one answer. So let us see if that is correct. Yeah. And then we have Young's modulus of the prototype is 200 GPa, and Young's modulus of our model is given to be 3 GPa. So we see now stress in our model is load in our model by the characteristic length of the model. Dimensionally, it will be Pm by Lm squared. Similarly, sorry, stress in my prototype will be P prototype by L prototype squared. Now this I can recast in another fashion. Essentially, I know that stress is E model strain in the model. Same I can do here, prototype. In other words, so from here I get this, and from here I get this. Now my idea is to have geometrically similar deformations. So essentially what I'm trying to say is this ratio must hold in order for me to have geometrically similar deformations. So what would this amount to? So my P model is essentially this into this. So let us say what this is. What is my Lm? It is 7. So 7 squared into Em was 3 GPa. GPa's would get cancelled, so that's fine. I'll just keep it as 3 by Lp is 15 squared, and this is 200 GPa, and my load that was applied to my prototype was 1000. So let us see what Pm comes out to be. 3 into 1000 by 15 squared into 200. So it comes to around 3.27 newtons. So if I were to apply 3.27 newtons with this scale, I can see that my strains would be geometrically similar. So is it clear, sir? 3.26. Yeah, exactly. Yeah. Yes. What is the question here, sir? Okay. 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 So this is nothing but my characteristic length. This is the load, and this is the Young's moduli of both these. So basically, in order for us to get geometrically similar deformations, we have back calculated what should be the load that has to be applied. Now, one thing has to be kept in mind, that 3 GPa, yeah, one thing that has to be kept in mind is 3 GPa that we have seen for epoxy, that would be at room temperature. Now, if we want to do stress freezing, we know that polymers have something called a glass transition temperature, where it basically leads to the rearrangement of matrices and all that. In which case, we should be cautious to have our similitude relations accounting for the reduction in its stiffness at that temperature. So there is a lot of literature available as to what the material properties of these polymers are at different temperatures. So once we arrive at the conclusion that we have to do stress freezing, we should calculate our loads according to the stiffness that it would have inside the furnace, not at room temperature. So that should be kept in mind. That is for stress freezing applications. So I hope that this is clear. Is it clear, sir, Mr. Rajamannar? And there are any questions here? Yeah, yeah. Okay. Okay. Yeah. Okay then. So let us look at the next question. In digital photoelastic techniques, the direction of principal stresses can be evaluated using which of the following methods? So the 4, 6 and 10 step are basically containing, these are all phase shifting techniques. And we saw that PSTs, also abbreviated at PSTs. So all PSTs can essentially calculate theta and delta over the model domain. Whereas if we come to RGB photoelasticity, it is also called three fringe TFP, three fringe photoelasticity. This essentially works on error analysis between application and calibration image. Calibration N, I can say. So once we have a application specimen that we have loaded and we are seeing the color, that is we are have captured the image and we have RGB at each and every pixel of that image. We will compare that error to what the same material gives in case of a standard problem such as 4-point bend specimen, where we know what is the fringe order at each and every point, and we will compare that RGB error in order to obtain what this is. So essentially, isoclinics cannot be calculated using RGB photoelasticity because those are not color dependent. Hence, they cannot be evaluated using RGB, or also called TFP. So this is only for isochromatic calculation. But in many applications, that is sufficient. For example, if we were to characterize cracks in fracture mechanics, we have to evaluate something called a stress intensity factor, in which case our whole field isochromatic data is sufficient to do that by running a least squares module. So I hope that this is clear. So isoclinics, essentially directions are nothing but isoclinics, and these can be calculated using phase shifting techniques but cannot be calculated using RGB photoelasticity. So I hope that this is clear. Okay, so let us look at the next question. In the analysis of 3D model using photoelasticity, secondary principal stresses vary continuously along the light path. Secondary principal stresses remain same along the light path. Direction associated with secondary principal stresses remain the same in every plane. Directions associated with secondary principal stresses need not be the same in every plane. So basically, what are these secondary principal stresses? In case of a 2D model, 2D model, whatever we see for plane stress or plane strain, the stresses are maximum in that plane only. So sigma 1 and sigma 2 that we see, assuming that both are positive, sigma 1 and sigma 2 that we see are real in that plane. Whereas in case of a 3D model, the orientation and magnitudes of actual principal stresses, that is sigma 1, sigma 2 and sigma 3, they need not be confined to that plane which is perpendicular to the light path. Needn't be confined to the plane perpendicular to light path. So essentially, crudely, if we were to say, these are what we see when we do slicing and we place it in a polariscope is essentially the 2D projections of those principal stresses, you can say. So that is why these are basically called secondary principal stresses, to differentiate them in 3D photoelastic analysis. So once we have this at every plane and we stitch it together, we can get the entire three-dimensional stress field as to how that is. That is meaningful. But for one plane, it is not right to say that the principal stresses are at that plane, at that point, and that plane are in that direction, because its orientation could be arbitrary and we are only seeing the 2D projections of those stresses in the plane which we have sliced. So I hope that that is clear. So yes, secondary principal stresses vary continuously along the light path. So at each and every path, we will be able to see that we will get different projections based on the variation. If they were same, essentially we are watering down to no response along the same response along the light path, which implies that it could either be a plane stress condition or a plane strain condition. So yes, they vary continuously along the light path, and directions associated with secondary principal stresses also vary continuously along the light path. Need not be the same. So I hope that this is clear. So if there are any questions, please do ask. Yes, okay. Right, thanks. Okay, so let us look at this question. In three fringe photoelasticity, or RGB photoelasticity as we call it, the RGB values at a point can be used to determine the fringe order n. A disk is subjected to diametral compression of load 700 Newton. Okay. The diameter of the disk is 60 and thickness is 6 mm. The RGB values and coordinates at 2 points A and B are given in the table. So these are given. This is the table. So essentially what we have done is we have loaded a disk under diametral compression, taken 1/4 of it, and at two select points A and B, which we know according to our calculated origin and magnification factor obtained from our image processing, we know that at these coordinates we can just type in from the image is nothing but a matrix of intensities. So once we separate out the red, green and blue plane, we'll be able to see at that pixel in the red plane what is the intensity, in green plane what is the intensity, and blue plane what is the intensity. So those intensities, these are nothing but light intensities. These are light intensities varying from belonging to 0 to 255 for each plane. For red plane, it will be 0 to 255. So once we have this combination, we can capture any color. Okay, so at those 2 points, from the image that was captured of the loaded disk, it was obtained that red, green, and blue intensities are these. Also, the grayscale representation is of the total fringe order evaluated using least squares color matching method in 3 fringe photoelasticity is shown. So this is shown. I'll explain what this is in much more detail. So this is shown, and we have been given a color calibration table. Use the color calibration table for some selected data to base your computations on and answer the following questions. So there are some questions. So we look at the questions, but first let me explain what we are trying to do. Now we know that from our standard calibration table, a point which has RGB in this combination, RGB with the red intensity as 165, green as 130 and blue as 156 pertains to fringe order 1.8. This is known from a known problem. This is developed from a known problem. Namely, that the 4-point bend specimen where the fringes are straight and horizontal. So essentially, once we know what the load we have applied, we can see what the stresses that are being formed, and we can count out, because in case of a 4-point bend specimen, we know the neutral axis sigma 1 minus sigma 2 is 0, so it will be black in color. And then as we go on increasing the load, for the case of a 4-point bend specimen, we will have sigma 1 minus sigma 2 at the center as 0. Then this will be the next fringe, which will represent sigma 1 minus sigma 2 equal to 1. Then sigma 1 minus sigma 2 equal to 2, and so on. So based on the variation along this line, let us say, based on the variation along this line, the green line starting from 0 till the end, we can know that we will load this model and capture an image. Now we will take this line and we will see at fringe order 0 what is the RGB combination. At fringe order 1, what is the RGB combination? So a table, this table is nothing but an extracted version of that, where we are seeing it from fringe order 1.8 to fringe order 2.12, how the red, green and blue intensities varied. So I hope that how the calibration table was developed is clear. Okay, now it is given that using 3 fringe photoelasticity, we will be doing a least squares color matching method. So essentially, we are trying to do error minimization. So what is the error here? Color matching. It is nothing but, let us take this to be my application image. So everything pertaining to the application image, I will write the subscript A. And everything pertaining to calibration image, I will write the subscript C. So it is nothing but difference in color. In application, difference in or rather difference in color between application and calibration. So why I'm doing root over? Because I'm essentially trying to calculate the square of the errors, because so that my whenever the error is positive and negative, it doesn't cancel out. I'm trying to sum up all of them and quantify it so that there is no compromise. So it is not a linear fit, it is a least squares fit. So how can I quantify the difference in colors? Essentially, any color is made up of is a specific combination of red, green, and blue. And conveniently, in my image processing, even our cameras, if you see, they have something called Bayer filters, which in which each and every pixel will have light sensitive diodes either to red, green, or blue. So once we capture this, we will be knowing red, green, and blue intensities at each and every plane. There are more sophisticated cameras with three color planes. Basically, they will give you faithful information of RGB intensities at each and every pixel. Whereas normal DSLRs are based on Bayer filters, which have some sort of approximation, some sort of averaging that goes on. Because it will not calculate R, G, and B individually at each and every pixel, it will skip one pixel to the other and interpolate the value midway in the middle pixel for each and every color. So that is how this works. So essentially, if I were to write my color matching method, I'm trying to calculate the error in application image minus calibration. I'll square it. Then RG, the green light intensity between application and calibration, and blue intensity between calibration and application. So my error is, this is my error formula. So this is essentially my error formula at each and every pixel. So each and every pixel of the image will have some RGB. We have been asked to calculate it at 2 points A and B, where we have been given what RA, RB, and essentially this is RA, GA, BA, and this is RC, GC, VC, and N at that point. Based on this difference, we will see wherever that is the minimum, we will match it to that particular N. Okay, so in order to do that, let me just perhaps open some Excel. I'll present my screen also. Okay, so I hope my screen is visible to you people. That is, the Excel file is visible. So let me write R, G, B, and N from the calibration image. So let us just fill this up quickly. It is 165, 132, 122, 99, 87, 88. Then if I were to go, this is given as 130, blue is 156, 172, 214, 232, 218, 184. And N is 1.8, 1.86, 1.93, 1.96, 2.04, and 2.12. So this is my calibration table. So far, so good. Okay, this is calibration. Now let us go to application image for point A. Okay, for point A, what is RGB that is given? For point A, R is 145, G is 127, and B is 200. Okay, so now let us write the error function. What is the error function? It is nothing but square root of square. So we just need to populate it with the difference minus this. Second will be blue minus blue. Third will be 156 minus 200. So this has given the error for the first column. Now let us do it throughout. So this is the kind of error that I'm getting. Now I can see if I were to plot this, let us say, so I'm able to see the plot is something of this sort. So the minimum error goes to 27. The third point, if I see, it goes to 27, which implies third point is 1.93. So this is the least error. So if I'll just put the error here. So these are my error values for point A. So I can see that 27, this is my least error, which would imply that the fringe order at point A, I can take it to be 1.93. Okay, similarly, if I were to do the same thing for point B, it is 99, 157 and 184. This won't be the least. I'm able to see, if I see my graph again, the least error comes at the penultimate point, which is nothing but 31, right? So this doesn't mean anything. It ends at 31. Okay, so the least error comes at the last point. If you see, it comes at 31. The graph is this way. So the fringe order for point B, this will be for point B. The fringe order for point B, we will take it to be 2.12. So I hope this is clear what we have done. If there are any questions, please ask. Then I'll start presenting my other screen and try to conclude the problem. Okay, so I take it that this is clear. I'll just stop presenting here. Yeah, so let us look at the questions, what they are. So the first question says, what is the minimum least squares error computed at point A? So we saw this pertains to the third point. Third row, I should say. So basically this row gives me the least error, which was coming to, what was the quantity that was coming there? 27 something. Yeah, 27.59. So the error was 27.59, which was the least. So based on that least error, can I conclude something on fringe order A? It will be pertaining to the third column. What is the fringe order there? It is 1.93. So the fringe order, initially I will assign the fringe order at point A is nothing but 1.93. Similar exercise we did for point B also, and we got the least error in the last row, which was coming to 31.95. So from the last row, this gave the least error for point B. You can see R, G, B and values are almost corresponding. There is no error in B because application image blue intensity is 184 and calibration image is also 184. So the errors were only in red and green. So we will take this to be the initial fringe order of point B. So NB, we will take it to be 2.12. So I hope that this procedure is clear. So the more refined our calibration table is, you can see that if there were 100 points between 2.04 and 2.12, it will be more refined. So our results will be more and more accurate. So essentially our graph will become more smooth. So that is the idea behind this. So I hope that this is clear. Let us look at the ask question. Abrupt jumps in the fringe order are visible here. Select the appropriate statements which explain this. So we can see essentially in a grayscale plot, we know that fringe order here at the outer boundary is 0 and fringe order increases like that. The fringe order gradient is this way. So what we should have got in from by plotting it from 0 to 255 is constantly it changes from black to pure white at the maximum load point. Whereas we can see that there are some white bands here. There is a white band here. There is some distortion here. So these basically indicate jumps. Why these jumps come about is the question. So stresses are discontinuous in some of the regions of the model. Is this possible? Since we are studying continuum mechanics, we cannot have abrupt jumps. Even if there is a geometrical discontinuity, the stresses at the far field will adjust itself so that it builds up a continuous variation in order to uh, a continuous variation towards the singularity. So there cannot be jumps in stresses. Strains are discontinuous in some regions. We are not dealing with strains as of now, and strains, since we are dealing with elastic bodies and assumption of isotropic and homogeneous materials, for strains to be compatible and give our smooth displacement fields, we will take it that these are continuous. So this is also not the reason. Colors of isochromatics repeat in some regions of the model due to deficiency in the system. Yes, exactly. What happens is basically after essentially RGB values, if you were to plot and see them, these are nothing but sinusoidal variations. So in which case it is possible that more than 2 points in our model domain can nearly have the same RGB combination because of color repetition. Color repetition in calibration table. So if we were to consider that our calibration table is like that, so let us say these represents the point where colors are repeated. So if our scanning scheme initially started here, fringe order it will report will be some n1. If suddenly this point was skipped and it identified the same RGB combination somewhere else, so it will give fringe order as n2. So there will be sudden jump in the fringe order, which is why simple color matching is not an effective way to to do this analysis. If the scanning was done over here, it will report it as n3. So there will be no continuous variation of n. So the remedy to color repetition is based on our fundamentals of continuum mechanics. We know that stress flow is continuous, in which case the flow of our fringes also needs to be continuous, in which case our error will also include that condition of continuity. So RA minus RC squared plus the entire color difference we'll write, and we will also have neighborhood point NP minus NC, and we will scale it with some factor. So essentially this will ensure that our abrupt jumps are taken care of. So this addresses color repetition. So what this will do in terms of this is, let us say our pixel under consideration was this, and then when and we got first we did a first level analysis like we did now with the color matching scheme, and we got the fringe orders at every pixel. Now this will refine it. Let us say that our pixel has reached this point. It will not only check the RGB difference, but it will also check what its neighboring pixel's fringe order is. If the fringe order here is 2, and simple RGB formula indicates that the fringe order here is 7 because of that color repetition, it will not pick that point because 7 minus 2, that error will be much more. So this is how it will basically do the refinement. So this is nothing but our refining scheme. This is called refined TFP. So for the procedure for this is, procedure was for conducting TFP is, first you do color difference, error based on color difference, and get first level estimates of n throughout the domain. Now once we have done that, if we were to plot it in a grayscale, we will see that certain areas will have some streaks. It won't be a continuous variation. That is because of color repetition. Then based on this, arrived at the n field that we have arrived at in the first step, second step would be dealing with refinement based on n in first step. So we know how the formulae are. This is the formula for refined TFP. We'll be doing that based on this. And for the initial case, this will be our formula to use. And then we will do something called smoothing in order to get a much smoother variation. Even the abrupt jumps will be cut down and we will get a smooth curve. But essentially, this will not affect your results. Your results will only get affected by the first two steps. So once we do that refined TFP, then we will be able to see that from black to white, we will have a continuous variation here. So that is the philosophy behind our three fringe photoelasticity. So to answer the last question, stresses colors in the isochromatics repeat in some regions of the model due to deficiency in the system. Yes, because it is not able to discern and there is a tolerance error for which you will have to proceed the algorithm. So all these play a factor in this. So color repetition essentially leads to this thing. Stress optic law is not varied in some regions of the model. We are trying to do whole field analysis in the elastic domain. So photoelasticity is definitely applicable. So stress optic law definitely holds. So that is not the reason. So I hope I've been able to give you some glimpse of what TFP was. So if there are any questions based on what we discussed in the last question, given that it was a little elaborate, I welcome them. I'll take them now. Okay, so I hope that it is clear what we have discussed about how RGB works. Please explain the question which I shared you in the mail. Okay, so we have a specimen like that. I don't know what the shape exactly was, but I take it this was the. Yeah, so to do fringe ordering, essentially take it that these two will be applied in the same line. So essentially, once we press this, we have been given a monochromatic image and asked to do fringe ordering. So for that, you have to figure out what happens at these points. Based on what we had discussed about a free surface and reiterant corners, this will give you a clue about what is the fringe order at this point. Once you know the fringe order at those points, you know that stresses are essentially continuous. So from continuum mechanics perspective, once you know for the first fringe, from the black and white image, you know how the fringes are varying. So you can count them out and order them. So that is the basic principle behind it. So I would suggest that you try it out. Yeah, thank you. Okay, so are there any other questions? Are there any questions based on this RGB which we discussed? I hope I've done some justice to explaining what we are essentially trying to do in this RGB. And there are software packages which incorporate this in a detailed manner. Those software packages were developed in the photomechanics lab at IIT Madras. So I'll also try to include a demonstration of how that is done for a simple problem along with the video that I post here. But other than that, I've essentially run out of questions. But I hope that I've given you some overview of what the 3D analysis and TFP and stress freezing is about. So if there are any other questions in this regard, please do ask. I'm happy to take them now. Okay, so other than that, if there are no questions, I would perhaps like to call it a day. I'll try to include one demonstration of TFP with the in-house software and tag it along with this video and post it. And if there are any questions from you based on what you have seen there, you are more than welcome to bring it up in the next session. So if there are no more questions, I'd like to call it a day then. Thank you. Thank you for attending. Thank you. Okay, so let me demonstrate a problem of a simple circular disk using this software DigiTFP. So let me set the problem directory. So I will select isochromatics, and there are other functionalities including isoclinics and isochromatics, which I'm not discussing now. So let me load the image of a circular disk. So this is the image of a circular disk I have generated using the simulation software pscope. So now we are able to see that here at the load application points it is showing as red. This is because it is a simulated image. In case of an experimental image, we will be seeing continuous fringe orders, albeit the fringe density will be very high. Okay, so now let me go ahead and make a mask. Mask is to basically cut out the regions which we do not want in the analysis. So for the purpose of this demonstration, I just want to show the middle portion as to how TFP performs. So I already have a mask, so I'll just load that mask here. So here I'm able to see that I have cut out portions from the top and bottom, and I'm focusing only in the middle portion. So there are ways and means to do this analysis for higher fringe gradients also using the same software. But for the purpose of this demonstration, I'll keep it limited to this area, this white area here over here. Okay, so now, so I'll be focusing on isochromatics. So this is the color adaptation option where we can do 1 and 2 point color adaptation. This will be useful for calibration tables that have been developed for different material or different tints as opposed to our application specimen. So let me go on to do this fringe ordering. I'll select a calibration table here, and let us use this RGB difference formula. So there are different algorithms available. So the simplest one being the RGB. So let us generate the FRL. So now This is interesting. I'm able to see that there are black and white alternating bands over here. On the right side, we are able to see that pitch black represents 0 and white represents 11. So why this is occurring is because of color repetition, as we saw in the live session also. So let me go ahead and refine it. So there are different algorithms that have been developed here for refinement. So I'll just use the FRSTFP algorithm here, and I'll select a seed point. Basically, I have to select at least one point where the fringe order is correctly shown. So that I'll be able to gauge with this information window. So let me go ahead and select a seed point. I know in the case of a disk under diametral compression that outer boundary is fringe order 0 and the first fringe would be fringe order 1. So if I hover my mouse over it, I'm able to see this n. So I'll just select it at a point where it shows a value which is close to n, close to 1. So I'm able to see the point here is 1.12 I have selected. So I will, and these are other methodologies that are available and a lot of publications have been made towards these. So I will not go into the details of these. So I'll just go ahead with refinement. So now I'm able to see that I'll just update this refine fringe order grayscale. Now we are able to see in this region of interest, which is marked by the red line, the fringe variation is continuous from 0 to somewhat of a higher shade of gray. So this is correctly refined. So if I were to see the isochromatics now, and if I were to pay attention to this n, as I hover the mouse from the free boundary, this comes out to be fringe order 1. This is fringe order 2. This is fringe order 3, and so on. When I go out of my mask, I'm able to see that it will give a constant fringe order of 0 because that is not under the purview of analysis as of now. So this is just a basic demonstration of how TFP is done using this software, which was developed at Digital Photomechanics Lab at IIT Madras. This has further functionalities on performing TFP and phase shifting techniques. Thanks.